Hello and welcome. This is the Chapter 4 summary. So let's review electrolytes. So the idea of an electrolytic solution is one that can somehow unite these two electrodes in the solution. If we were to connect them with a wire, then the light bulb would light up. It turns out we can use things that contain ions when they dissolve in solution, like salt, and then those ions are going to act as a wire to allow the light bulb to light up. So we call a solution that contains ions to be an electrolytic solution. So sodium chloride obviously leads to a solution of sodium cations and chloride anions, and then those ions are uniting the electrodes, allowing the light bulb to light up. So any solution that fully ionizes would be strongly electrolytic. So a strong electrolyte is a solute that fully dissociates in water. A weak electrolyte is one that only partially dissociates into water. A lot of compounds that dissolve in water that don't allow the light bulb to light up at all, things like table sugar do this, would be termed non-electrolytes. So a non-electrolyte is a solute that mostly or does not dissociate at all in water. So a weak electrolyte does a partial dissociation, so we get some ions, just not a whole lot. So a weak acid is a good example where we get some formation of ions, but not as many as we would if it were a strong electrolyte. So we get some ions, so we get some lighting up of the light bulb. And then some compounds are just insoluble in that they don't dissolve in water at all. So of course they're not going to have any ability to impact the light bulb lighting up if that compound simply doesn't dissolve. So an insoluble compound is not a solute in the solution, therefore it doesn't dissolve, therefore it can't possibly make ions within the solution. So let's review strong electrolytes, a compound that completely dissociates in water. So our two key examples are our water-soluble ionic compounds, so maybe KNO3, water-soluble. So in water, this compound really exists as potassium ions, each individually surrounded by water, and then nitrate ions, each individually surrounded by water. And then these polyatomic ions are remaining intact, they're not dissociating in water further. And so then another example would be a strong acid. So if we had something like HNO3 in water, it would really be existing as a 100% H plus ion surrounded by water, and then nitrate ion surrounded by water as well. Now, HNO3 is a molecular compound. It's an acid, and it produces H plus ion, so we call it a strong acid. So it's a strong electrolyte, water-soluble ionic compound, or water-soluble compound that's a strong acid, so it's a strong electrolyte in water. KNO3 is an ionic compound, so it acts as a strong electrolyte because it is water-soluble. So we might remember our solubility chart. All our alkali cations, ammonium cations, nitrate, and acetate ions, with no exceptions, anything paired up with those ions is water-soluble. And then we have the chloride, bromide, iodide usually soluble, sulfate usually soluble with a couple exceptions. And then sulfide hydroxide usually insoluble, but with some exceptions. It's the alkali and ammonium cations plus calcium, strontium, barium. And then carbonate, phosphate just have the only exceptions that we know are soluble already, the ammonium and alkali cations. So now everything else for the ionic compounds would just be insoluble. So if it's an ionic compound, it's either behaving just like KNO3, fully dissociating, and it's a strong electrolyte. So the only examples of a weak electrolyte are going to come from the molecular compounds. So these are going to be our weak acids and bases. Okay, and we'll have another summary slide of this in a moment, but a weak electrolyte that partially dissociates in water, that's a weak acid, might be something like acetic acid, CH3COOH, dissociates, loses one proton, forms the acetate ion, plus H+, and then we don't lose any more of these H's, so those H's are non-acidic hydrogens, they remain intact, attached to the carbon. Think about it this way, if you remove those hydrogens, you know how to name the resulting anion. If you don't know how to name that anion, it's probably because it doesn't actually form in aqueous solution, so therefore we don't need to learn how to name those sort of things. So acetic acid is a monoprotic acid. It's a weak acid. You get a partial dissociation, so we use the backwards arrow to indicate that we get some of the acetic acid molecules remaining intact in the solution, and then we also get some formation of the ions. So if you imagine having 100 molecules of acetic acid, it's probably, 95 of them remain intact, and then 5 of them dissociate. So you get a couple ions in solution, but not as many as you would get if it were a strong acid. Then ammonia is our prototypical weak base, reacts with water to pull a proton off of water to produce NH4 plus ammonium plus hydroxide ion, and it just does so partially. It just doesn't do this reaction completely. So we therefore term NH3 to be a weak base, and it's only pulling 1H plus off. We tend not to give a term to the bases like monoprotic, but it's just pulling 1H plus off of water, making hydroxide ion. If we recall, precipitation reactions are when we mix two solutions generally containing soluble salts, and then they're mixed, and then an insoluble salt is produced. The solid is called a precipitate. So the example that's being done here is Pb 2 plus is being added through a solution of lead nitrate, so you have lead ions and nitrate ions in the solution, and then you're also mixing that with Ki. PbNO3 is water soluble, so we might write PbNO3 is water soluble. That's reacting with Ki, also water soluble. And then we really are just mixing these ions together, and that when the I minus bumps into the lead ions, that they start to precipitate. So if you take 2 iodides and a lead, they're going to start precipitating that yellow solid. So we're going to form PbI2. That's an insoluble precipitate. That's one of the insoluble iodide salts. And then the other product is going to be the KNO3, so potassium nitrate, which is water soluble. And so if we want to balance this out, it's going to take 2 KIs. We're going to get 2 KNO3s to give us our PbI2. Okay, so now the PbI2 starts forming these layers, if you will, of plus and minus ions separating from each other. They're more dense, so they drop to the bottom of the beaker. And then the solution remains on top that contains our spectator ions, the K plus and the nitrate ions. They remain in the solution. So we originally started having all these ions in solution. So we had 4 ions in solution. Then we mixed them together, and then we ended up precipitating 2 of the ions and leaving behind the other 2 in this reaction as spectator ions. So K plus and NO3 minus remain after the reaction simply dissolved in the solution. So how to predict whether a precipitate forms? So note the ions present in the reaction. Consider the possible cation-anion combinations. So you started probably with 2 water-soluble compounds, so you're considering switching out the minus cations with each other and considering if you get something that's insoluble. You got to use a solubility chart. Now we do provide that on exams, so you can look that up online. In the daily quiz area, I have a solubility chart like one that you'll be provided with on midterms. So now let's consider the mixing of magnesium nitrate and sodium hydroxide and think if we get a reaction that will take place here. So what we're really doing, we can think of this 2 ways. We're taking MgNO3 to water soluble. It's a nitrate, so we know it's water soluble. NaOH, also water soluble. And we're mixing this and considering forming MgOH2 plus NaNO3. Now we know NaNO3 is going to be water soluble, so we'll write AQ. Now for MgOH2, magnesium is not one of the exceptions for hydroxide, so this is not soluble, so this would precipitate as a solid. So this is going to precipitate from the solution and then allow this reaction to occur. So we'll need 2 NaOHs to balance out to give us the 2 hydroxides, and then we'll need 2 NaNO3s to put this all into balance, and then we have 2 nitrates on both sides. Now, another way that we can see this reaction taking place is just kind of considering that if we have strong electrolytes, so I'm kind of thinking here, are my reactants strong electrolytes? Because if they are, they're fully ionized. And then we might think of, well, the solution really contains magnesium ions, nitrate ions, sodium ions, I'm just keeping my balancing, and that we're then forming MgOH2. This is not a strong electrolyte, so we keep it intact. That's kind of the point here, is that it remains intact. And then our NaNO3, 2Na plus NO3 minus, 2 of them. So our nitrate ions are spectator ion, or sodium ions are spectator ion. We could cancel them out and just write Mg2 plus 2OH minus forms MgOH2 as our net ionic reaction. So we can do things like write reactions. We can write full molecular. We can write the full ionic. We can write the net ionic. We can identify spectator ions. And then as we get through the chapter, we're going to see that we can solve problems. Once we know concentrations of our reactants, maybe we can figure out how much product forms using the ideas very similar to a chapter 3 problem with that unit of molarity that we'll be discussing a little bit more a little bit later in this video. And so we could do the same thing with the PbNO3 reaction, but I think I'm going to skip this discussion here because I don't think we need to have much more of a discussion because, you know, like we could probably pretty easily identify that our solution is lead ions, nitrate ions. Let's picture it this way. Let's use this slide to kind of picture the reaction this way. So you have your lead ions, your nitrate ions in solution, you have your K plus ions, I minus ions, and relatively some ratio here, we're going to form our PbI2, and then KNO3 remains in the solution. So we precipitate our PbI2 and keep our KNO3 in solution. If we picture the reaction this way, hopefully we can see the spectator ions in this reaction are K plus and NO3 minus, and then our net change, our net ionic reaction here will be Pb2 plus reacting with 2I minus forming PbI2 insoluble solid. Let's review our strong acids. We have to memorize the 7 strong acids. So 7 strong acids, HCl, Br, and I. And then HNO3, HClO3, HClO4, and then the first H plus from H2SO4. So only that first H comes off 100% in a solution of sulfuric acid. So those are our 7 strong acids. We just have to memorize those so we can identify all other acids from naming. You know, so some examples would be HF, acetic acid, phosphoric acid. Notice that the strong acids are only the X. Not all the X, but there's no us. So all the HClO2, HClO, H2SO3, these are all examples, including others, of weak acids. Now our strong bases kind of break the category of all the other strong acids, weak acids, and we'll see weak bases, in that they are going to be ionic compounds. Our acids are molecular compounds, or weak acids are molecular compounds. Our strong bases are going to be ionic compounds. These are going to be the hydroxide-containing soluble hydroxide salts. So these will be things like NaOH, CaOH2, etc. So these are just the water-soluble salts containing hydroxide ion. So these are ionic in their nature, and that just by virtue of them being water-soluble means they're releasing hydroxide ion into the solution, and a base is anything that makes hydroxide ion in solution. So for like NaOH in solution, it's really sodium ions and hydroxide ions. So anything producing hydroxide is a base. If we make a lot of it, it's a strong base. So our water-soluble hydroxide salts are making at least 1 mole of hydroxide ion per mole of that solute. Calcium hydroxide is actually making 2 moles of hydroxide for every 1 mole of calcium hydroxide. So we get a lot of ions, a lot of hydroxide ions in this solution. Our weak base is something like NH3 because it reacts with water to produce at equilibrium, forming NH4 plus and hydroxide ion. Now we might also identify anything that kind of looks like N, say R3, or maybe R is equal to like a methyl group. Other groups here. Now these are more things that you'll see in OChem, but just kind of showing you that there are other examples of weak bases. And they just contain maybe things like, for example, like you might see NC2H3, 3. And we can identify that as being a base in a similar behavior as NH3. But not likely that you'll see too many examples like that in this class, but you might see more of those in OChem. So a summary of our behavior of common soluble ionic and molecular compounds. So again, this is, I think, the third time I've shown this chart, once in the intro video, once in lecture, and then now here, that this chart here is assuming that you have a soluble compound, then comparing the behavior of ionic versus molecular soluble compounds. So if you have an ionic compound that's water soluble, then the only type of electrolyte you get is a strong electrolyte, because an ionic compound is only dissolving in solution because you get the formation of ions and the dissociation of the salt. There's no examples of weak or non-electrolytes for soluble ionic compounds. If it's an insoluble ionic compound, there's no solute in the solution, therefore there really isn't a solution, it's just water, and water is non-electrolytic, so the solution remains, the solution remains like not lighting up the light bulb, if you will, thinking about whether or not we light up a light bulb. So then, for molecular compounds that are water soluble, all of the strong acids lead to a strongly electrolytic solution because we're making ions. We're making things like H plus and Cl minus ions, or H plus and nitrate ions if we have a nitric acid solution. So the key is that strong acids are molecular compounds in their nature, and then if we know it's a strong acid, we're getting the 100% formation of that acid into its ions. And then weak acids and weak bases form weakly electrolytic solution because they're making some ions. So if you have like 100 molecules of ammonia in a solution, you might get 5 of those that are making ammonium and hydroxide ions at any given moment, and the rest remain as a neutral ammonia and water molecule. Same thing with like HF. So our examples here, NH3, HF, etc. Those form weakly electrolytic solutions. Then if you have any other molecular compound that's dissolved in water, it should be a non-electrolyte in the solution. So some examples would be the alcohol, so say ethanol. Ethanol, you might think it releases hydroxide ion. It doesn't. You might think it releases H+. It doesn't really do that either. If it did, we'd probably would have named it as some sort of acid. And so that's not forming any type of solution that is electrolytic. Another example might be things like glucose, C6H12O6. So there's other compounds that contain only nonmetal elements that simply dissolve in water but do not form any type of electrolytic solution. So an electrolyte is any substance that dissociates into ions when dissolved in water, and a non-electrolyte dissolves in water but just simply does not dissociate. So let's consider some acid-base neutralization reactions. So we could write that HCl plus KOH forms KCl. We get a salt plus water is our usual product for an acid-base reaction. This salt is water soluble. We can write AQ, liquid for water, AQ, and AQ. When we start thinking of net ionic reactions and writing those, think about how HCl exists in solution. Is it a strong electrolyte? It's not whether it's AQ, it's whether it's a strong electrolyte. If it's a strong electrolyte, we can dissociate it in the solution so that we can imagine if we mix HCl, it's really H plus and Cl minus ions. KOH is really K plus and hydroxide ions, and then that forms K plus and Cl minus ions and water that remains intact. So as soon as the H plus and the hydroxide bump into each other, they form water, and then water never goes back into the ions because it's a non-electrolyte. So our net ionic reaction for this reaction would be H plus OH minus goes to H2O liquid. Then we have the example of HNO2 plus KOH. They still react together, so even though we have a weak acid now reacting with a strong base, we still get the formation of the products that we expect. We get our salt and water, so KNO2 is our salt, and then we get H2O liquid. Now the difference here is that HNO2 is a weak acid, weak electrolyte, so it doesn't dissociate into water when we begin with that solution. So think when you're mixing HNO2, how do we best describe HNO2? The answer is as the molecule of HNO2 intact. Then we take K plus and OH minus as our best description for the strong electrolyte, strong base KOH. So we have a strong electrolyte, so we separate those into its ions. Think about how KOH would exist by itself. Is it best to describe it still with the K and OH intact or separated? Obviously separated because it's a water-soluble ionic compound. Same thing with KNO2, K plus, NO2 minus separated, and then water together So our net ionic reaction here is only going to drop the K+. So hydroxide ions are going to have to bump into the acid, grab the H, form water, and then leave behind NO2-. So that's our net ionic reaction. Only one spectator ion of K+ for this particular reaction here. And then for the last one, we did this one in class 2, that we're going to take 3 KOHs and form K3PO4 as our salt, and then plus H2O. We're going to get 3 of them. And then the idea here is that H3PO4, weak electrolyte, so remains intact. So even though it's aqueous water soluble, you may wonder, we predict solubility trends of ionic compounds. The only other things I would say that you know for sure are water soluble are the small alcohols, sugar, and then these weak acids, strong acids, and NH3, the weak base. And so we can take those AQ, but we keep the molecule intact because it would be intact because it's a weak electrolyte, not a strong electrolyte. So we keep that intact, break up the KOH, because that's how KOH would exist in its own solution. Then we'd form 3 K plus cations plus PO4, 3 minus plus the 3 waters. So our net ionic reaction here, again, only drops potassium. And we keep the 3 hydroxides, H3PO4 forms phosphate plus 3 liquid waters. Let's review some oxidation numbers. So, oops, I made a mistake here. This should be PO4 2. But so calcium 2 plus, PO4 3 minus. Our oxidation number for calcium would therefore be a 2 minus. Now the O ordinary rules, it's a 2 minus with 3 exceptions. The 3 exceptions for O are that the peroxides, O has a -1 oxidation number. The superoxide oxygen has an oxidation number -0.5. And then compounds with fluorine, this is neither of those, so we know oxygen has its ordinary number of -2. So the other O's would just be the ordinary oxidation number of -2. And so then for a phosphate ion, probably the easiest way to do this is work out what P has to be to make the math of 4 times -2, and then factoring in whatever phosphorus's charge is to give you the overall charge of -3 for the phosphate ion. So that means phosphate should have an oxidation number of +5, so we can subtract 8 for the oxygen's oxidation numbers and come up with -3. So phosphorus would have a +5 oxidation number. Most of the halogens are -1, except when they're paired up with fluorine or oxygen. So one simple example might be like ClF3, negative for fluorine. Fluorine's always negative, so we go -3 for the Fs and then +3 for the chlorine in that example. So bromine here is just -1 for the normal oxidation number of a halogen, -4 for the 4 of them, so +4 for carbon. NaO2, we know sodium is a +1. That means we have a -1 spread across the 2 O's, so that's a -1/2. So that's sodium superoxide, and so that kind of comes back to where the oxidation number of oxygen in superoxide is -1/2. So oxidation numbers are a per atom description. So the normal rule for hydrogen is that it's +1 in molecular compounds, -1 in ionic compounds. So we get a +3, so we have to have a -3 for nitrogen. And then for CSH, we go +1, that's an alkali metal, so hence we get a -1 for H. And again, H should be -1 when paired up with metals, +1 when paired up with nonmetals. Our activity series is showing us the relative reactivity trends, that the metals towards the top of the chart are more reactive, more likely to undergo oxidation and exist as their cations in solution. And if we were to mix these with, if we were to mix these metals with these cations below, then what's going to happen is the solutions are going to give their electrons off to these metals to go back to their neutral charge state. And then likewise, if we were to mix instead these cations with these metals, nothing really is going to happen at all. So if we were to take gold and say, well, gold's never giving its electrons up to something like magnesium cations to go back to magnesium. So the utility of this chart is to be able to predict reactions. Like if I take magnesium 2+ and then react that with gold, that no reaction ends up occurring because magnesium is not reactive enough. Gold is not very reactive. So now imagine the opposite scenario happens. Imagine we take a solution of gold 3 plus, which would be a very precious solution to have made because you would have basically ruined a nice gold sample. And so then imagine mixing that with magnesium solid. Now magnesium is more active. It should give its electrons up more easily. It forms magnesium 2 plus, loses 2 electrons in the process, giving those electrons back for gold to reform gold solid. Okay, now we got to put this into balance, so maybe we'll do 2 gold, so that's 6 electrons absorbed by the gold and 3 magnesium cations forming. If you picture this being AuCl3 for like maybe somewhere where we're getting these like chloride, the balance of the 3 plus and the 3 minus, and you're forming MgCl2, you might then see the balance of the 6 chlorines versus the 6 chlorines before and after. So the balancing is maybe easier done when you counter ion pair the charges is sort of the main point here. But the bigger message though is seeing that gold 3 plus is down here, magnesium's up here. Magnesium's more reactive, so it should be able to react. And then when I'm looking at this reaction here, that gold is less reactive than the magnesium, so it doesn't react when we mix the magnesium cation with the gold solid. You just have to kind of think your way through this problem, think which is more reactive. We should have a more reactive metal react to form a lesser reactive metal during the reaction, not the opposite. I shouldn't take a less reactive metal and form a metal out of the more reactive metal. So it's all about using the relative reactivity trends. So let's use the activity series. If you need to peek at it, you might look at some other chart, but I chose 2 examples here where we know potassium is relatively high in the chart, silver is relatively low in the chart. Your precious metals are at the bottom because they're less reactive. You wouldn't want to choose a precious metal as a reactive or highly active metal. That wouldn't make a whole lot of sense. So potassium should readily be able to lose its electron to form K+. If it did so, it would form KNO3, AQ, and then while silver reforms silver metal. Okay, and so as written, this reaction would be balanced. So this reaction can occur because we're taking a more active metal and forming a lesser reactive metal in the process. Okay, and so then if I try to do the opposite and take silver metal, which is not very reactive, and try to form a more reactive metal, an AgNO3, that doesn't seem to make sense. So I can write the products, but then I could quickly recognize that potassium is more reactive than silver. So if I formed a more reactive metal, it would just react back with the silver nitrate and then go back to what we began with. So the more reactive metal is more likely to react, and that more reactive metal is potassium. So we're not going to reform potassium if I take silver and KNO3. So it's sort of like predicting the reaction here. We can predict which way we can mix K and Ag together, so I can take a solution of silver plus and K0, zero charge, and then have them react together. If I do it the opposite way, then they don't react at all. So we get no reaction for the middle reaction here. And then lastly, let's go back to AgNO3 KCl. This is now a metathesis reaction. So when I'm seeing 2 salts mixed together instead of an element plus a salt, then I'm just thinking metathesis. So this just brings me back to the early reaction from the chapter, that being the exchange of the ions. So we get something that's insoluble. We do. AgCl is insoluble, so it's solid, precipitates from the solution, and then we get then the other product being KNO3 aqueous. So this reaction occurs, but it's not an oxidation reduction reaction because everything remains with the same oxidation numbers. What changes here is the formation of a precipitate. So we just have a metathesis reaction going on here. So this is just being shown that the reactions could look similar, that the top reactions are not metathesis. They're the oxidation reduction reactions are what we're considering for the top reactions. So let's talk a little bit about concentration units. Molarity is just defined as the moles of solute dissolved in the volume of solution, usually in liters. Our common unit of M is 1 mole of that solute per liter of solution. Okay, so we're told we have 37.5 milliliters of a 1.50 molar solution of HCl is diluted to a total volume of 2.50 liters. So imagine what we're doing here. We're taking some container, maybe it's a round bottom flask, and then we're going to put 37.5 milliliters of the HCl in here, and then we're going to fill it with water and allow them to mix, and then we're going to fill it to maybe some line where that's indicating 2.50 liters. Okay, so one of the things we might do is say, well, for this initial solution, the number of moles of HCl in that solution, I could calculate that just by taking the 1.50 moles of HCl per liter of that solution, and then we're using 0.0375 liters of that solution. So the initial HCl solution that we're starting with here contains 1.5 times 0.0375 moles of HCl. So that's 0.05625 moles of HCl. Okay, and so then what I'm basically doing is saying, well, instead of having 37.5 milliliters of the solution, so if I just divide this by 0.0375 liters, that just takes me back to the 1.50 molar. Instead what I'm saying is we're now replacing this volume by adding water, where the water doesn't contain any more HCl, it's just pure water, so I'm just increasing the volume of the solution now to 2.50 liters. Now we have to be sort of clear that we're diluting to a total volume of 2.50 liters. So this is probably taking, about 2.5 minus 0.0375. So it's like we're mixing about 2.46 liters of water with the 37.5 mils. So we're not adding 2.50 liters of water, we're just adding enough water to make the total volume of the solution 2.50 liters. So I take the moles of HCl, 0.05625, and then divide that by 2.50 liters, and that gives me a concentration of 0.0225 molar. Now one of the keys is the molar would be moles of HCl per liter of that solution. So that's what the big M means. So 0.225 big M moles of HCl per liter of that solution. So I've now decreased this concentration from my starting concentration. It was 1.50 molar, now it's just 0.0225 molar. Now titration is a technique we can use to determine an unknown concentration of a solution. So maybe we have a solution where we have 20 mils of an acid solution, but we don't know the concentration of acid in the solution. Imagine this is maybe like an HCl or an HNO3 solution. So imagine we have like a solution like HCl. We don't know the concentration, so the number of molar it is, we don't know. We can add a couple drops of an indicator. The way an indicator works is if we have an excess acid solution like we have, maybe it's clear. And we start adding sodium hydroxide dropwise. So we have like HCl reacting with NaOH, and then we're adding the sodium hydroxide slowly. We're forming NaCl plus water as our product. So as the reaction's occurring, we have an excess of acid. So we have an acidic solution, and we're adding this dropwise. So we keep adding and adding and adding. Then eventually when we add that last little drop of NaOH that we need to complete the reaction, the solution turns into an excess base solution and then changes color. So just the way that the technique is a way so we can figure out for the amount of HCl present in the solution, what's the exact quantity of NaOH that we need to add to add that correct stoichiometric quantity. So we get that color change the moment we add enough moles of sodium hydroxide for every mole of HCl present. Based on this reaction, we have to add 1 mole of sodium hydroxide for every 1 mole of HCl present. So we use a burette so we can carefully determine the volume before and after, so we can calculate the volume of sodium hydroxide delivered. And you just have to know the concentration of that KOH or whatever or NaOH solution it is that you have that you're titrating. So imagine you know the concentration of this. So say you know the milliliters that you add, you know the molarity of that solution before you start, and so then you can figure out the moles of sodium hydroxide and then therefore the moles of HCl that had to be present. We'll do a couple examples of that in a moment. So how titration works by having a volume of some standard solution that it takes to reach the equivalence point. That's just some color change. You know the molarity of that standard solution, so you can calculate the moles of the solute in your standard solution. So this would be like the example of HCl plus NaOH forms NaCl plus H2O that we were just talking about. So you know the molarity of the solution, you know how much volume it takes, so you can calculate the moles of NaOH. You can use the stoichiometry of the reaction to convert to the moles of the solute in the unknown solution that had to be present. And then from the initial volume of the solution, you may say, well, maybe we had some big container of HCl. We took a little portion of it to test, and then we want to know the concentration of HCl in that big container. So maybe you have like 2.5 liters of HCl, and you want to check its molarity. So you take maybe 20 mils of it, 20.0 milliliters of it, and test its concentration using a titration. So you're usually starting with some solution you want to know the concentration of through this process. Okay, a slight typo in this question here. We forgot to specify a 20.00 milliliter solution of HCl. So imagine you have a 20.00 milliliter solution of HCl, and this solution requires 33.5 milliliters of 0.100 molar calcium hydroxide to be fully neutralized. What is the concentration of the HCl solution in units of molarity? Now the first thing is kind of conceptualizing what we're doing here. Imagine maybe you have like a 10-liter stock solution of HCl, and you want to know the concentration of that stock solution. So maybe you take a small portion of it to test. So you take 20.00 milliliters, use a pipette to accurately measure out that volume. So then you have your acid solution, and then maybe you start adding the base solution with that burette. So you use a burette to deliver the calcium hydroxide dropwise. You already know its concentration. Maybe you know this concentration because calcium hydroxide is a solid at room temperature. Maybe you can dry it very carefully and then add it to water and then calculate its molarity very easily. And so maybe we have some way of knowing this concentration easily ahead of time, and then we figure out with our burette how much volume it takes to add to the acid solution to cause that color change to take place. And so at that point, we know that we've added the proper number of moles of calcium hydroxide to react with HCl. What we have to know here is how to write this neutralization reaction. We have HCl, calcium hydroxide, both water soluble, AQs. Both of these are strong in their strong acid, strong base. We're going to form the salt CaCl2, also water soluble, and then plus water. Only key here is that I'm going to need 2 HCl's to put this in the balance. And then I'm going to form 2 waters. Now this 2 is very important here because this is telling me that for every 1 mole of calcium hydroxide that had to be added, that means there are 2 moles of HCl present in this solution. And then I want to know the concentration of HCl in this original solution before we sort of began the titration process. So when I want to know the concentration of HCl, the brackets indicate the concentration of what's in the middle. So the concentration of HCl would be the moles of HCl in that solution divided by the volume of the solution. The volume of the solution, we're told, is 0.0200 liters. I'm just converting over to liters because the big M is mole per liter. And then the moles of HCl, I can calculate here by taking the volume and the molarity of the calcium hydroxide solution. So I think I'm calculating the moles of HCl, starting with the 0.100 moles of calcium hydroxide present per liter of that solution. And then I use 0.0335 liters of that solution. And then that would give me moles of calcium hydroxide. Then my stoichiometry says for every 1 mole of the calcium hydroxide that we had to add means that there were 2 moles of HCl present. So then I just take the moles of HCl and then divide by the volume of the HCl solution. So 0.1 times 0.0335 liters times 2. So that means there's 0.0067 moles of HCl originally in that solution. Divide that by 0.02, and then I get 0.335 moles of HCl per liter of that solution. And that would be 0.335 big M. So the solution is 0.335 molar HCl. Now let's do a quick check here. If I have 20 mils of that solution, so 0.02 times 0.335 is 0.0067 moles of HCl. For every 2 moles of HCl, I need to add 1 mole of CaCl2, so I can divide by 2. So I have to add 0.00335 moles of calcium hydroxide, and it's 0.1 mole per liter. So I can kind of calculate back to the quantity of calcium hydroxide as a double check here. Okay, so 0.335 molar in the case of HCl. All right, now another type of titration problem you can do is you can start with like a dry, unknown acid. Maybe you know something about it. Maybe you know it's a diprotic acid. So imagine you start with this acid that's a solid. So you have a powder that you know is a pure acid. If you want to know the molecular weight of the acid, the thing you would probably do is say, well, the molecular weight or the molar mass would be the mass of that sample. We know it's 1.25 grams. Divide by the number of moles of the acid in the compound. Okay? So if you knew how many moles there were in this sample of your acid, you could figure out the molecular weight. Just because you know it's 1.25 grams, however many moles it is, that's going to give us the answer to our question. Now, the issue here is that because it's a diprotic acid, I know there's 2 H pluses per whatever the counter ion is, just whatever that is, it's a 2 minus. Doesn't quite matter what it is here. Now I'm going to react this with KOH, because that's what it says. We're adding KOH, and then we're going to know that you need to add 2 K pluses to make the K2A. Should be water soluble, but that doesn't quite matter. H2O liquid. It doesn't matter in terms of getting the right answer here. So I take the H2A, I'm going to need to add 2 KOHs so I can form 2 waters and then a K2A. So the whole idea here is diprotic acid is going to take 2 KOHs to balance this reaction out. Now what I want to try to do is solve for the number of moles of that acid in that sample by taking the quantity of the known amount of KOH that had to be added to it. So I take the 0.01052 liters of that solution. That solution is 0.115 moles of KOH per liter of that solution. So liters cancel. I get moles of KOH. For every 2 moles of KOH that we had to add means that there was 1 mole of the H2A present. And then we can calculate. So go 0.1052 times 0.115 divide by 2. So that works out to be let me make this a little smaller, 0.0006049 3 sig figs moles of the acid. We know that there's that many moles of acid now in that 1.25 gram sample of the acid. So 1.25 divide by that answer. I get 206.6, round that to 207 grams per mole. Or 207 AMU per 1 single molecule. Okay, so those are a couple examples of things you might do with a titration or titration-like example, and we're really just using stoichiometry here. One of the keys is when you see a titration problem, I see that probably number one mistake I see students make when they do a titration problem incorrectly is they forget to consider what the reaction is. So whenever you're doing a titration problem, try to consider what's the acid, what's the base, how do they react together, because almost certainly you're going to need to figure out that stoichiometry of how many moles of the acid pair up with the base. In this case, it's 2 moles of KOH for 1 mole of the H2A for the second example. And for the first example, I had to add 2 moles of HCl for every 1 mole of the calcium hydroxide. So at some point in a stoichiometry problem, you're going to need to have some sort of balanced reaction written out in order to be able to solve the problem correctly. All right, that's all for this video. Thanks for the attention.